Good day students. Today we are learning about the recursion in data structures using C. Okay, now see here recursion. What is recursion? So recursion is a problem solving approach which can generate a simple solutions to certain kinds of problems that would be difficult to solve in other ways. So recursion splits a problem into one or more simpler versions of itself. Okay, then sometimes the best way to solve a problem is by solving a smaller version of a exact same problem first. Okay, recursion is a technique that solves a problem by solving a smaller problem of the same type. So see here, for example, factorial of a given number, powers, or a greatest common divisor. So we call it as, and these are examples for recursion program. Okay, then after go for the next one. The recursion function always contains one or more terminating conditions. A condition when a recursion function is processing a simple case instead of the processing a recursion. Okay, and without the terminating a condition, the recursive function may run forever. So simply we call it as a self-calling. Okay, so here we have one example here, towers of Hanoi. So the towers of Hanoi is in a mathematical puzzle which consists of three towers like pegs we call it as and more than one ring and as a Dept. These rings are of different sizes and stacked upon an ascending order. The smaller one is sits over the larger one. Okay, so this is the logic for the tower of Hanoi. So there are the other variations of the puzzle where the number of discs increases. Okay, so how we can see it now? See here, this is the tower, and we have three pegs. Okay, so 1 and 2 and 3. So these are the discs. See, the discs are larger. First one is a large one and the second one is a smaller, and then of the smaller one. Okay, this is the ascending order. So we can make it as a descending order also. So depends upon the logic. Okay, now see here, the mission is to move all the discs to some other tower without violating the sequence of arranging. So we should arrange that by using these three towers. Okay, so few rules are followed for the tower Hanoi are the only one disc can be moved among the tower at given time. We should move only one disc only at a time. Okay, then after only the top disc can be removed. Only we can remove the top disc. Okay, and no large disc can sit over the small one. So we should place always a smaller only. Okay. See here, tower of the Hanoi puzzle with n discs can be solved in a minimum n-2 and -1 steps. Okay, this is a representation shows that a puzzle with 3 discs has been taken into 23 minus 1 equal to 7 steps. Okay, see how. Now algorithm. See the first algorithm. See the algorithm. To write an algorithm for the tower of Hanoi, first we need to learn how to solve this problem with a lesser amount of discs. Say 1 or 2. So we make 3 towers with the name, sources, destination and axis only to help moving the discs. Okay, if we have only one disc, then it can be easily be moved from source to destination peg. Okay, see, under here we are placing the disc to one to another by using the other towers. Okay, now if we have 2 discs, here we have replacing the 2 discs, then first we move the smaller top disc to the axis peg. Okay, then we move the larger bottom disc to the destination peg. After that, and finally we move the smaller disc from the axis to the destination peg. So we are playing this game by replacing all these discs. Okay, one after one, and we should only place the lowest one at the top. Okay, then after go for the next one. See, this is the picture. First one is the source. See, in the source we should place the biggest one first and the smallest one to the top. Okay, this is the destination or axis. See here, so now we have the positions to destinate an algorithm of tower of Hanoi with more than 2 discs. We decided the stack of discs in 2 pairs. The parts disc, the largest disc, nth disc in the one part, and all other n-1 discs are in the second part. Our ultimate aim is to move disc n from source to destination and then put all other n or comma 1 disc onto the it. So we are imagined to apply the same recursion way to all given at the set of discs. So this is called as a recursion self-calling program. Okay. So the steps as follows are: step 1, move n-1 disk from source to axis, or move to nth disk from the source to desk or move 3. So n minus 1 disk from the axe to destination. Okay, this is the process of moving disks. Then after see, a recursive algorithm for the tower of NOE can be derived as follows. First, see the algorithm first is with the starts. Okay, then after procedure NOE, disk and source and desk and axe. So first is the disk, the round we call it as a disk, and one is the tower of source and one is the tower of destination and one is the tower of axe. So if the disk greater than 0, then the greater than 0 means have a certain value greater than 0. Then NOE disk minus 1, source, axe, destination. This is a step 1. Okay. Then after move the disk from source to destination. This is a step 2. Then after NOE disk minus 1, axe and disk source, step 3. So this is the NOE steps of 1, 2, 3. Always we play with that is a source to destination or axe to the replacing the disks. Okay. Then after C, here first loop will ends and the procedure will ends. This is the algorithm for the algorithm of a tower of NOE. See the next one, approach. See here in the approach, take an example of 2 disks. Here we are taking 2 disks. Okay. Let rod 1 equal to A and rod 2 equal to B and rod 3 equal to C. See step 1, shift the first disk from A to B. First we are shifting the disk A to B. And step 2, shifting the second disk from A to C. Okay. Now we are placing the 3 values. Okay. Then after shift the first disk from B to C. So already we have a B. B have some disk. We are placing that to the after of C. After that, these replaces will be activated. So the pattern here is the shift n minus 1 disk from A to B, shift last disk from A to C, and shift n minus 1 disk from B to C. We have so many games. We will use these algorithms. Okay. See the next one. Imagine the illustration how this will be placed. See in the top of the structure. Here is A, B, C. This is a place. Okay. A have a 3 disks. Okay. The green color, white color and red color. First we are placing the first disk, red color disk to the C. Okay. Then after C, the second, we are placing the second one to the B. Again we are placing the A value to the C. Okay. Then after we are placing the C value, and here we have a same values, A value, B value, C value. Okay, now here in the tower of C we get the largest one. This is a destination one. Okay, again we are using the B. In the B, red color will be placed on the A rod. Okay, after that we are placing the B's white color to the green color top. Then after red color we are placing the red color disk. After that we will get the answer. This is the example of 3 disks. Okay. Then have to go for the next one. See here the input values, the input to output disk 1 moved from the A to B and disk 2 moved from the A to C. So disk 1 moved from A to C and input 3. So in input 3, output disk 1 moved from the A to C and disk 2 moved from A to B. It will same like in the way disk 1 moved from C to B and disk 3 also moved from A to C. After that, disk 1 moved from the B to A and disk 2 moved from B to C and disk 1 moved from the A to C. See in the next one, linker representation of stacks. So in the linker represent, already you know about the stacks and know about the linker list. Here we are representing the stacks with the linked representation. How we can use? See, instead of using array, we can also use the linker list to implement stacks. Why? Because the linker list will randomly stores the data. So memory representation will be easy in the linker by dynamic memory allocation. Okay. So linker list allocates the memory dynamically. So time complexity in both the scenarios is the same for all the operations like a push, pop and pick. So in a linker list implementation of stack, the nodes are implemented non-contiguously in the memory. So we can randomly we can pick the, so the system will pick the random or reusing the data. Okay, the random means here it picks the not a continuous memory, it picks wherever the empty space, empty memory it picks it. Okay, randomly it stores the data. Then after each node contains a pointer of its immediate successor node in the stack. After the stack is used to be overflow. If the space left in the memory heap, it is not enough to create a node. see the representation. Top 4800 is in storage. Okay, see here 33, 22 and 11. The stack representation, the first element is in a down and the last element is in the up of the stack. So having three elements, top different so these are the addresses. See them. First one is the null address and the second one is the address and the third one is the address, because this is the linked list. So linked list representation means we can store the data randomly, but it gives them a stack order. Okay, we are making that program, adding a node to the stack. So we call it as a push operation. So adding a node to the stack is referred to as a push operation. Pushing an element in a stack is a linked list, implemented in different from that of an array implementation. But here we are using a stack representation with a linked list. In order to push an element on the stack, the following steps are involved. Create a node or first allocate memory to it. If a list is empty, then item is to be pushed to the start node of the list. So it is the first element. Okay. Then after, if there is some nodes in the list already, then we have to add the new element in the beginning of the list. This is the task to us, to adding a node to stack. Okay. See here the representation, time complexity. See, in the time complexity of the stack representation is first create a temp variable and assign 44 into the data field and the top in the link field, and it is the last temp assigned to the top. Okay, deleting a node from the stack also is there. See the next one, pop operation. We call it as a simply deletion of the pop element. So deletion of pop element means a stack pop element means a deleting element of the node from the linked list implementation. Stack is different from that array implementation. Here the pop an element from the stack, we need to follow the following steps. So here we have two steps. One, click for the underflow condition. What is the meaning of underflow? So the underflow means occurs when the try to pop from the already empty stack. So if the stack is empty, we can't delete an element. Okay, then adjust the head pointer accordingly. So the head of the stack, we are adjusting the head of the stack. See, in that the stack, the elements are popped only from the one end. So therefore the value stored in the head pointer must be deleted and the node must be freed. So the node of the node and now becomes the head of the node. Always the top is the head of the node, and always we can delete the top and add the top element only. Okay. Then after go for the list, time complexity. See here the pop three elements, top link, under link equal to null. So free temp, automatically it gives either freeze the element. So that's we get the single element only here. Then after go for the next one. Display the nodes. We call it as a traversing. So display all the nodes of the stack needs a traversing all the nodes of the linked list organized in the form of stack. For this purpose, we need to follow the following steps. First, copy the head pointer to the temporary pointer. Move the second one, move the temporary pointer to all the nodes of the list and print the value of field attached to every node. Time complexity O for n. Okay. Then after go for the linked representation of queues. We know about the queues. Queue have two edges like front part and right part. So here we can add or delete the elements in the both the ways, and we have different types of queues. Okay. Here in your queues, in a linked queue, each node of the queue consists of two parts. We call it as a data part and link part. So first we call it as a data part and link part. Here each element of the queues points to its immediate next element in the memory. Okay. Then after the linked queues, there are two pointers maintained in the memory like a front pointer and a right point. Okay. So this is a starting point and ending point. See, the front pointer consists the address of the starting element of the queue, while the right point contains the address of the last element of the queue. So that's why we call this in a front part and right part, or a starting part or ending part. We call it as an head and tail. Insertion of a deletions are performed at right and front and respectively. So we have so many different types of queues. We can perform that actions. Then after, if a front and right both are null, it indicates that the queue is empty. So nothing is there. That's why we call it as an empty queue. Okay. Then after go for the next one. See the link represent of a queue. See in the picture, 9 is the front part. 9 after we have one more element 2, 1, 7, 4. In the 4 right part, because that is not linked another part 1. Okay. See, this is called as a linked queue. Operations of a linked queue. There are two basic operations which can be implemented on the linked queues. The operations are insertion and deletion. So simply we know the insertion means we are inserting an element and deletion means we are deleting an element. So in the linked queue. Okay. See how we are using that both two. First one is the insertion operation. We are inserting an element. See, the insertion operation append the queues by adding an element to the end of the queue. Like the new element will be placed or last element of the queue. Okay. There may be two scenarios of inserting this new node of PTR. So this the new element may be replaced into the linked list. Okay, placed in the linked list. In the first scenario, we insert element into the empty queue. So the queue is an empty, so it is the first element. In that case, the condition front equal to null becomes true. Then the new element will be added to the only element of the queue. Okay. The next is the next pointer will be indicates the null value. Okay. Go for the next one. If the second case, the queue contains some elements, okay, maybe one or more elements, the condition in front equal to null become the false. So after getting the false scenario, we need to update the end point array to the next pointer of the array will be point to the new pointer PTR. Since this is a linked queue, since we also need make to the array pointer point to the newly added node PTR, we also need to make the next pointer of the array point to null. Okay, then after see the algorithm how they will follow that. See, step 1, allocate the space for the new node PTR. Then after set PTR equal to data equal to value. If front equal to null, the front part is null, then set front equal to rear equal to PTR. So it is the first element. So it is the front element and it is the rear element. It is a single element of that linked queue. Okay. Then after set PTR equal to next, the next condition, the linking variable array next equal to null. So it replaces the null value. Okay. Then after go for the next one. Else maybe have some value. So if you have some value, then set rear equal to next equal to PTR. So it replaces the next value. Okay. It continues the first to next element. Set PTR equal to set rear equal to PTR and set rear equal to next equal to null element. So this is the conditions of inserting a linked queue. Okay. Then after go for the next one. So we saw the insertion. Now we can know the how we can delete the element. So we can delete the element by deletion operations. Removes the element that is first inserted among all the queue elements. So first in, last out. So here firstly we need to check whether the list is empty or not. If the list is empty, so front equal to null became true. If the list is empty, then this case is simply write underflow. So underflow means no elements are there. Otherwise, we delete the element that is point by the pointer front for purpose of copying point to the front point into the pointer PTR. So shift the pointer element to the next node and freeze the first node. Okay. See how. Step 1, if front equal to null, so it writes a underflow, no elements are there. Go to the step 5. Step 5 is end of the if. Okay, it completes the entire task. Okay. Otherwise, maybe the list has some elements. Okay, we are now deleting some element. We call it as an set PTR equal to front. Okay, so now we are dealing first in first out front element. Set front equal to front to next. Automatically front elements will freeze and the next element will be the front element. Okay, now free the front element. This is the deletion of linked queue. See why we are using this linked list and queues means by using the data structures we can make the instructions loading or deleting by using the different types of operating systems. Good day, we will meet again.